Let's talk about the idea of escape speed. So in our notes, let's write this down, that we're going to find the escape speed for an object projected off the Earth. It turns out, if you launch an object at a certain speed, it will leave and never come back. So let's consider how we can analyze such a situation. First, let's think about it from a forces perspective. So once you release it, what force is acting on it? Yeah, of course, the force of gravity, just the force of gravity. And then as the object gets farther and farther away, what happens to that force of gravity? Sure, it's going to decrease. As r gets larger and larger, the force of gravity gets smaller and smaller, and since it's the only force acting on it from sigma f equals ma, if the force gets smaller and smaller, that means the acceleration gets smaller and smaller as well, which means we can't use kinematics, right? Kinematics is out. So what should we use? Let's think about it from an energy perspective. So once we launch the object, what force is acting on it? Of course, the force of gravity. And what kind of force is the force of gravity? A conservative force, right? And so motion driven by conservative force, we can do the law of conservation of energy. Energy is pretty much always our go-to when kinematics fails us. So we can start with the law of conservation of energy. We just have to keep in mind we're talking about some really, really large distances. So for potential energy, we're clearly not going to be using mgh. We're using the other one, negative g, big M, little m over r. So let's consider our initial and final conditions. The initial condition is when the object is on the Earth, and we're going to launch it from Earth. And then the final condition is when it's really, 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 really far away, really approaching infinitely far away. So we need to remind ourselves, when we're talking about the astronomical scale version of gravitational potential energy, we had that stipulation that as r approaches infinity, the gravitational potential energy goes to 0. Remember, that's our common 0 point, which means when this object is really, really far away, we're going to say the final potential energy is 0. Set that equals 0. It's infinitely far away. Now, we also want to find the escape speed as the minimum speed to launch the object. Obviously, we launch it any faster than that, it'll go and obviously just keep going. But we want to see, like, the object just barely gets there, just barely gets far enough away that's not going to come back. And so, taking the limit of that, we're going to say that when it gets there, what's its speed? Well, we want to sort of take the limiting case of it just barely gets there with no extra speed left over, which of course doesn't make a whole lot of sense, but this will give us a minimum speed in the beginning, right? So the final speed is going to be 0, so the final kinetic energy is also 0. It just barely gets there. This is a bit of an interesting situation because it's saying that the total energy has to be 0, right? It has to add up to 0. How could this possibly happen? Well, let's remind ourselves that if we replace these terms here with their equations, kinetic energy is, of course, half mv squared. Gravitational potential energy, well, that equation has a negative sign in it. And so if it has a negative sign in it, this is going to be okay. Right? And so it's going to be negative big G, big M, little m over r. Here I'm replacing one of those terms of the mass with the mass of the Earth, because that's one of the terms of the interaction. The other mass is the mass of the object. And then radius of Earth, well, that's going to be the starting position measured from the center of the Earth. That's where we're launching it from. Okay, so we're just going to work some algebra magic here, moving that over to the other side. Here I'm replacing V0 with VESC for escape speed, and we're going to solve this equation for that escape speed. So why don't you just pause the video and just go ahead and do your algebra. Of course, we see the mass of the object drops out, and we just rearrange, and we're going to get this, the square root of 2 times big G, mass of the Earth, over raised to the Earth. These are terms we have. So you can look back in previous problems for the mass of the Earth and the raised to the Earth, and go ahead and put the numbers in. And let's go ahead and calculate the escape speed. Okay, so when we put all the numbers in, we should be getting 11,200 meters per second, or 1.12 times 10 to the 4th meters per second. So the idea here is that we launch an object at that speed, it should leave and never come back. Now, of course, there are other things to contend with, right? There's all the air resistance and friction, things like that. So really, this is a very minimum speed. We have to really launch at a much larger speed to contend with all the losses to non-conservative forces. But this does give us a sense of just how fast you have to launch an object. Why is this important? Well, it turns out NASA actually did this. Back in the 70s, they launched the Viking space probe with the intent that it would leave and not come back. And so they did this calculation, and then, of course, added a little bit extra speed to it, so it would contend with all the losses. But the idea is it launched it, and then the point was it would leave and maybe be found by some other civilization out in the universe somewhere. And so the Viking space probe is coded with all sorts of information about the human race. There are diagrams there of what we look like, and there are diagrams of the solar system and the planets there, and like big arrows pointing to the third planet saying, we're here, we're here. Now, that's not exactly what it looks like, but the point is that there is information so that if some other civilization were to find us, they can maybe contact us. And trying to figure out what would be the universal language, everything is coded in binary, figuring that any advanced civilization would be able to decode binary, figure out how to translate that into whatever language they use, and then they can maybe find us and communicate with us and maybe visit us. Now, of course, if you believe Professor Hawking, who said that if we ever were to contact another civilization, we probably pretty much don't want them to contact us, because what would they want? Well, they probably want the same thing we do, to possibly colonize us, and so they may be hostile. But in the end, the probe is out there, and the probe does send a signal, and we collect that signal, and we just, recently we found that the signal is still working, which means the space probe is out there somewhere, hasn't been found yet. Maybe someday it will.